Chapter 6, Formation of Solar System. So the question is, what does the solar system look like, and what condition was presented in the early solar system that now we have this type of arrangement? So the solar system exhibits clear patterns of composition and motion. So let's talk about them. So if you remember from chapter 1, we were talking about how tiny planets are compared to the spaces between them. And so we had this example of sun being in the size of a grapefruit, right? And then so Earth would be 15 meters away in the size of a top of a pen. So we had this before. If you don't remember, please go ahead and watch those videos, previous videos that we were talking about a 10 billion times smaller. And so how the next star would, if this is in Washington, D.C., how the next star, the closest star to us, which is the Alpha Centauri, will end up being in San Francisco. So there are a lot of empty space here, and we will talk about what could cause the empty space and what happened to the gases between Jupiter and Saturn or Uranus and things like that when we get to chapter 11. But if you don't remember this simplification, please go ahead and watch those previous videos. So the center of our solar system, the sun, it is nearly 99.8% of the mass of a solar system. So the sun itself is more than 99% of the mass of the solar system. That's amazing. And just the comparison between Earth and the sun, this would be a great comparison for their size. About 1 million Earth will fit inside the sun. And the sun is mostly made of hydrogen and helium. And so it's basically what it does, it's converting hydrogen to helium, which is not allowed in normal condition. And we'll talk about this in chapter 11. So it nearly converts 4 million tons of mass into energy in every second. Mercury, which is the closest planet to the sun, it is made of metal and rock. It has a very large iron core, and so it is very hot. It has the biggest change in the temperature during the day and the night is for this particular planet. At the day, it will go all the way to 425 degrees Celsius, which is about between I think 800 to 900 degrees Fahrenheit. And during the night, it goes all the way down to 170 degrees Celsius below zero, which is incredibly cold. Remember, the North Pole and South Pole on Earth, which is pretty cold, will probably get down to -50. And so this goes all the way down to 170 degrees below zero. Venus, second, it's nearly identical in size to Earth. However, we cannot really see its surface because it's covered mostly by clouds. It has a hellish condition because of the extreme greenhouse effect. We'll talk about it in chapter 7. And what it means by the greenhouse effect, and because we also have greenhouse effects on Earth. It's just there are elements for this greenhouse on Venus that makes it very unique. So it's the temperature is really unique, and so it's even hotter than Mercury, even though it's further away. So and it has a steady temperature, about 470 degrees Celsius, all day and night. Doesn't matter. It's because of the greenhouse effect. We have Earth, so far the only planet with liquid water and with existence of intelligent life. And so we have oddly, we have a large moon compared to our size. So if you wanted to compare moon and Earth to their actual size, this would be a relative picture here. But it's very surprising, like how we are the only terrestrial planet with a moon, and not only with a moon, but we also have a large moon. So that's a question of why and what happened, and we can talk about it later. So another 2 videos that I will upload for you. Mars, it looks almost like Earth, except that it's almost dead, meaning that there aren't many geological activity going around it anymore. It has the biggest canyon and the biggest volcano in the entire solar system. There are some evidence of riverbeds on its surface, which means that it has a past liquid water history on its surface. Now, what happened to those waters, where they are today, how come it's not active anymore like what we see on Earth? We will talk about it on chapter 6 when we talk about these four terrestrial planets in very details. So, and then if you even zoom a little bit more out, we start with Jupiter, so which is the first big giant planet. It's much further from the sun. It is mostly hydrogen to helium, just similar to what we see in the sun. But so it doesn't have any solid surface. So in other words, these are all clouds, what you see. So there is no solid surface. It's liquid. And so it's 300 times more massive than Earth. And it has many moons, and it also has a ring, but we don't really associate a ring with Jupiter. But all of the Jovian planets, Jupiter, Saturn, Uranus, and Mars, they all have rings, and we'll talk about it in chapter 8. Now, Jupiter's moon, uh, there are many moons that Jupiter have, but the most famous ones called Galilean moons. These are the four moons that Galileo observed with his telescope. And so this one that you see is Io, which is the most active volcano in the entire solar system. It's all covered with volcanoes, more than 100 active volcanoes on its surface. So unlike Earth moon, Io is pretty active. We have Europa, which we believe it could have a subsurface ocean below a freezing um, surface. There is a liquid water. We believe it might be really the case. We have Ganymede, which is the largest moon in the entire solar system, and we have Callisto. So if you wanted to remember these names, I always remember when I was taking astronomy class, our professor was always saying, I eat green corn. That's how I remember it. Io, Europa, Ganymede, and Callisto. You can probably use the same thing. It's up to you, but that's the way I remember them always. Saturn, it is giant. It's just gaseous. It has spectacular rings that we can observe from the Earth. It has so many moons, and Cassini spacecraft studied it. Very detailed study. And so you can see the one of its moons, Titan, is actually has an atmosphere. This atmosphere contains methane and ethane, so that's why it's a little bit blue, greenish, bluish color. That's the only moon in the entire solar system with a thick atmosphere similar to what we see on Earth. So these rings are not is they are solid bodies, and countless of them. There are millions of these objects. They're very, very tiny, or some of them are really big. But they are always in a specific region with respect to the um, Saturn. In other words, their position with respect to Saturn will not change. The Saturn and ring moved together with respect to us, so that's why we see the position of the ring will change in different times. But in reality, the position of ring with respect to Saturn doesn't change. It's just our own perspective when we're observing Saturn. So I was talking about the Cassini studying it. It actually arrived in 2004. It was launched in 1997. So it had a flyby Venus 2 times, and it had a deep space maneuver to gain velocity and momentum. And so it passed the Earth one more time in 1999. And so it passed Jupiter to gain more momentum in 2000. And so it finally arrived to Saturn in 2004. Now, Uranus, it's smaller than Jupiter and Saturn, and but it's still much larger than Earth for sure. It's also made of hydrogen and helium, so they're gaseous and they're icy, but there are also some hydrogen compounds. water, ammonia, methane, ethane. But one of the mysterious things about this planet is that it has an extreme axis tilt, which is about 98 degrees. So it's really weird. What happened to this? So it's, in other words, it's rolling on its side as it's moving. And it's really mysterious for all of us today. We believe what happened to this could be a very giant impact that caused a severe change in its rotation. So it has a similar axis tilt probably to Jupiter or Saturn, but through a very massive collision with probably a big giant exoplanet or something like that, it 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 changed some of the parameters for Uranus. So we're still studying it. Neptune, you can see the ring is visible. Again, all of them have rings. It's just for some of them are more visible than the others. It is similar to Uranus in terms of composition, but definitely not the axis tilt. It also has many moons. So so all of these Jovian planets, Jupiter, Saturn, Uranus, and Neptune, these are very similar. We also have Pluto and other dwarf planets, and that's the category that we put them from now on. So since actually 2005. So Pluto is not a planet anymore. So it is much smaller than other planets. It is icy, so it has a comet-like composition. And Pluto's moon Charon is also similar, and it's actually very big. So with the concept that we have from our moon rotating around Earth every 28 days or so, what we think is that maybe Charon is doing the same thing. Is it moving around Pluto? No. They both move around a common center right here. So they both move around a common center. The reason is that this moon is big enough and it's very comparable to the size of Pluto itself. So they all move together. And that's not the only moon. Up to 2012, actually, we found more moons that are rotating around Pluto, but they are very small. So the biggest one is Charon here that you see. So we talked about planets that are tiny compared to the distance between them. And each world has its own character. Each planet is different, but there are some clear patterns in our solar system that we will talk about. So we want to know really, looking at the current solar system as is, how can we switch time back 4.5 billion years to understand the solar system when it was very, very young? Can we integrate time and push everything backward? Can we create a model with final condition as is today, and that model give us the initial condition? Can we do that? We want to talk about some of these, not in a very detailish form, but let's go ahead and get started. So one of the things that we realized when we were looking at our solar system, that all large bodies in our solar system, they orbit in the same direction, all nearly in the same plane. So if you're looking at the solar system from its side, you can see that it's all lying in the plane, which is called the plane of a solar system, or ecliptic plane. Not only that, they're also moving in the same direction. So sun is moving around like that. And you will do a homework on chapter 11 to calculate the rotation speed of the sun. And it's pretty easy to do, actually. So sun is rotating counterclockwise. Planets are also doing that. They're rotating around sun counterclockwise. Not only that, but they're also rotating around their own axis counterclockwise. Okay, there's some exceptions, but this is the majority of the planets or bodies in the entire solar system is doing this. It's very unique. And there are two major planets. We have terrestrial planets, rocky planets, and we have Jovian planets, which are icy planets. So they have a different size, the compositions are different, everything is different about them. And we also have comets. So if we zoom even further out, so this blue line here, this blue orbit is orbit of Neptune, which is about 30 AU away. So here is 30 AU, here is 50 AU, 30 to 50. So this disk is 20 AU, this distance. And this is Kuiper belt. So 30 to 50 AU, as you can see here. And more than 100,000 comets are there. Some of them as as even big as an entire city on Earth. Um, if you zoom out up to hundreds of thousands of AU away, all the way possibly to the next solar system, you have this spherical distribution of these objects, and this is called Oort cloud. We have not been able to directly observe the Oort cloud yet. We will probably in 2022 with James Webb Telescope. But so these are the reservoir that Oort cloud comets are originating from. So we also have that. It's interesting. We have two major reservoirs of these comets. But there are some notable exceptions. We talked about them a little for a little bit. But so we have a large moon, which we cannot explain, and we also, I mean, there are some theories that are saying, okay, Earth had a collision with a Mars-sized object, and so that caused these objects to go and start rotating, and eventually they accrete and form moon. But that's what a possibility. It's not for sure, right? And so for Uranus, we were claiming the same thing. They had a giant impact. That's caused an axis tilt. All right, so these are some of the patterns that we see, but we know that according to nebular theory, our solar system formed from a giant cloud of interstellar gas. And so nebula means just cloud. So these clouds are enormous. They're big. Take a look. This side is 100,000 AU, and AU is just astronomical unit, 93 million miles, which is the average separation between Earth and Sun. Now, these clouds are enormous. They're big. It's just unbelievably, several solar stellar systems can form out of these clouds. And the other thing is we have galactic recycling, meaning that when a star is born, through thermonuclear fusion inside the star is producing heavier elements, turning hydrogen to helium, turning helium to something else, right? Heavier and heavier. Eventually, when it goes crazy, okay, and through a supernova, this will put all of these elements, heavier elements that are now being created inside the sun in space. These heavier elements that are now being created will be part of another planet, will be part of another star, will be part of another object in the universe, right? This has happened many times in the past 13.8 billion years. So in other words, when you're looking at heavy elements on Earth, they couldn't just form on Earth. They have to have formed somewhere else. So that's very interesting. So we see the other star formation regions in interstellar gas clouds, which leads to support the nebular theory. All right, so we've seen it in other solar systems before. All right. That's the part that I'm going to stop for this part of the video. Part 1 is done. We'll just go with part 2 next. Okay, stay tuned.